In this video, we're going to talk about set notation, and we're going to talk about subsets. But what I want to do first is talk about how to generate a set recursively. And we're not going to use this idea straight away, but when we come to logic in week 4, and when we think about how syntax trees are made, the process is very similar, so I just want to get a rough understanding of how this works. So don't worry too much about this right now, but just think about the logic behind it. Now remember, recursion is just about taking a rule and taking some things and then repeatedly applying the rule to get, say, an infinite number of things, or to generate a lot of different possibilities. So for instance, with a sentence, we have, of course, we start with an S when we build our trees, and then we have a rule that says S goes to an NP and a VP. And you might have an NP goes to an N and a PP, and then a PP goes to a P and an NP, and just using these three rules and S, we can generate a sentence, or at least part of a sentence. We can generate a tree with it. So what you need to generate a set recursively are two things. You need an initial condition. You need something you start with. So with our example, what we're going to do is we're going to create a set containing all the numbers from 1, 2, 3, 4, and that goes on infinitely. So as an initial condition, I want to start with the number 1. So we're going to build this set of the natural numbers n, and we're going to start and say that 1 is an element of our natural numbers. Now, we need a rule. And what the rule is going to do is it's going to say, based on what we have in our set already, we can add something new to it. So we're going to use some variables for this. So our variable is going to say that if we have some number x, so this is just a variable, if x is in our set of natural numbers, then what we're going to do is we're going to add x plus 1 into our set of natural numbers. Now I know I'm using x plus 1 and x, so some of you might be a little freaked out about this because, Trevor, you said there's no numbers. It's just an example. So you don't have to do this yourself, just an example. But let's follow along with the logic. So with these two things, with this fact 1, 1 is an element of the natural numbers, and fact 2, if x is an element of the natural numbers, then x plus 1 is an element of the natural numbers, we generate all of the numbers from 1, 2, 3, 4, all the way up to infinity. Why? So here's our rule. Let's put our rule in action. If 1 is an element of the natural numbers, then our rule says that x plus 1, so 1 plus 1, which is 2, is an element of our natural numbers. Now we can use the rule again. Because 2 is an element of the natural numbers, then we find that 3 is an element of the natural numbers. And we just keep on using this rule forever and ever. So if we keep going, we get like 713 is in the natural numbers, therefore 714 is in the natural numbers. And that just keeps going infinitely. So that gives us our entire set where n starts at 1 and builds all the way up infinitely. Now, we can use this for syntactic structures. I'm not going to show you that right now because at this point it's just a method of generating sets that I want you to realize and to learn the logic behind. But when we do propositional logic, when we're building trees for sentences, we're going to see this in action. So for now, I want to talk more about set notation. In the last video, when we had a set, we just listed all of the elements in our set. So we would write like A, B, C, D, E, F, G, H, I, J, K, and so on. Or if we had vowels, we wrote A, E, I, O, U. We just wrote everything out. Now this is called list notation because we just list all of the elements in a set. Now this is nice if we have a few things and we know exactly what those things are. But sometimes we have a lot of things. Sometimes we don't know exactly what the elements are, but we want to be able to talk about a set. For that we use this thing called predicate notation. And in order to use predicate notation, what we do is we describe the elements of a set using a variable and a description. So here's what the form looks like. Instead of having, say, just a bunch of things separated by commas, we have this form. So we have a variable, we have this bar that is read as such that. We repeat the variable, and then we give it a description. So I have a concrete example here for you. Here's the set of all of the English consonants, and we're going to call this C. So C is our set. Now in list notation, how we did it in the previous video, we just write out all the consonants. So we have B, C, D, F, G, H, J, K, L, MNPQRSTVWXYZ. Okay, this is a bit of a pain to write out. This is only 21 things, but imagine if we had 2,000. Now, there's a much more convenient way of doing this. If we want to talk about the English consonants, why don't we just build a set based on the description? So here's another way we can write this. We can say C is the set of X such that X is a consonant in English. So these two sets that we wrote are exactly the same thing. In list notation, we write out all the elements one by one. In predicate notation, we just give it a description. These are the set of things X. Whatever X is just a variable. And whatever that variable is, it's a consonant in English. So how you can think of this is that your variable runs through literally everything in the universe. And when the thing that it encounters is a consonant, it fills it in. So when X sees A, for instance, it says, well, A is not a consonant, so A doesn't get added to the set. Then it sees B. Well, B is a consonant. Okay, so B is added into the set here. Okay, next it finds C. It checks C. Well, is C a consonant in English? Yeah, it is. So then C is added to the set. And this continues on and on and on until everything in the universe has gone through and we get our set, C. So this is useful when you have a lot of things in a set, or if you don't know what the elements are. So for instance, I can talk about all of the different people in Vancouver. I can have a set of Vancouverites. Now, I can't do that in list notation, because I don't know all the people that are in there. I don't know all their names. I don't know who's in there right now, but it's a set I might want to talk about. I might want to talk about the set of Vancouverites. So a good way of doing that would be with set notation, or with predicate notation. So if I want to talk about the Vancouverites, I could write, okay, Vancouverites, this is the set of, well, how do I describe people in Vancouver? Well, I use a variable, I'll just use X. So the set of X such that X is a Vancouverite. Okay, so what's going to happen is our variable X is going to go through literally everything in the universe. And when it encounters something that is a Vancouverite, it's going to add it to the set Van. And it'll be the same thing as the set Van written in list notation. But the difference is, with predicate notation, we don't have to know exactly what's in it. We don't have to write all the elements out. But we're still describing the same set as if we were to write out all those things. So predicate notation is very powerful. And usually when we describe large sets, or when we talk about groups of people, so the set of dogs, we wouldn't write out all the names of the dogs. We just write out the set of X such that X is a dog. If we want to write out the set of things that are happy, we write the set of X such that X is happy. With verbs, well, if, say we want to write the verb of everyone who's sleeping, well, the set of X such that X is sleeping. It's much easier than writing out the names of everyone in the universe who are sleeping right now. Okay. So that's a bit about predicate notation. We'll use that when it's convenient, but for now, a lot of the things we do are going to be in list notation still to get us comfortable with sets. The first thing we want to talk about are subsets. So when you have a set of things, let's call this set B. You know, in our case here, we have 1, 2, and 3. When we talk about a subset, what this means is another set that is contained within B. So for instance, I could have another set that is just 1 and 2, and I call this A. Now in this case, we say that A is a subset of B, which is written with this symbol here, if all of the elements in A are also in B. So the formal definition is at the top. A set A is a subset of a set B, if and only if every element of A is in B. So looking at this notation in list notation over here, in this first line, A is the set 1, 2, B is the set 1, 2, 3, and C is the set 1, 3. A is a subset of B. So this means that if we take all the elements in A, we should find them in B. So 1 is in A, and 1 is also in B. 2 is in A, and 2 is also in B. Therefore, because everything in A is in B, we see that A is a subset of B. Visually, what this means is that we can draw a circle around those things, as we did here with A, and that circle will be contained within B. Now let's take a look at C here. So okay, I'm going to get rid of A here just for convenience, and I'm going to do C in red. So C is the set containing 1 and 3. Visually, I can just draw a circle around 1 and 3, call this C. Okay, because I can do this, I know that C is a subset of B, because the circle containing all the things in C is within the circle containing all the things in B. And if I look at this in list notation, okay, 1 is in C, and 1 is also in B. That's good. 3 is in C, and 3 is also in B. So because everything in C is also in B, C is a subset of B. Now, I want to focus on just A and C at this point. So let's get rid of some of these things. I'm just going to write out our elements here, 1, 2, and 3. Now A contains 1 and 2, so let's do that in blue. Here's A. C contains 1 and 3. Well, let's do this in red. Now, in this case, A is not a subset of C, so we draw a little line through our subset symbol, and we see that C is not a subset of A. Why? Because if we take a look visually, well, 2 is in A, but 2 is not in C. Part of the circle for C goes outside of A. And we know C isn't a subset of A because 3 is in C, but 3 is not in A. That circle is not inside A. So if we just take a look at this in list notation, we can say, okay, well, 1 is in A, therefore 1 is in C. But 2, well, no, 2 is not in C. So because every element in A is not in C, we don't have a subset relation here. And that's the same vice versa. So if we look at it vice versa, then of course we have that 1 in C is also in A. But if we do 3, well, 3 isn't in A. So because 3 is in C but not in A, then C is not a subset of A. Now one thing to note with this notation is that this symbol here, this subset has a line under it. And think of it just like the less than or greater than sign. Sorry, less than or greater than sign. Less than or equal to sign. In this case, 3 is less than or equal to 4. But 3 is also less than or equal to 3. The numbers can be the same here with the less than or equal to sign. It's the same thing with a subset. So if I have B is equal to the set containing 1, 2, and 3, and I have D is equal to the set containing 1, 2, and 3, well, B is a subset of D, and D is a subset of B. The elements are exactly the same. And when the elements are exactly the same, both of the sets are subsets of each other. If we draw this out visually, well, let's do B in blue, and let's do D in green. They're overlapping sets. The circles are contained in each other's circle, or they're the same circle. So in this case, this is a subset. Now I show you this because we have this notation called a proper subset. And a proper subset must have less elements. So it's equivalent to the less than sign. So 3 is less than 4, but 3 is not less than 3. And you can see here with the proper subset symbol, there is no line underneath it. It's just the subset sign without that line underneath. So let's draw our elements here. So we have just 1 and 2 this time, and we have D, E, and F. Okay, let's circle D. We'll do that in red. Okay, D just contains 1. And let's take a look at E. We'll do E in green. E contains 1 and 2. So because D is within E, and D is not the same size as E, it's not the same thing as E, we know that D is a proper subset of E. Now, it is still the case too that D is a subset of E as well. So D is a proper subset of E, and D is also a subset of E. But let's not take a look at D anymore. Let's get rid of D there. Let's compare E and F. So E is 1 and 2. Let's do F in blue. F is also 1 and 2. But F and E are the same thing. They're the same set. They both contain 1 and 2. They both contain the exact same elements. They both contain the same number of elements. So because of this, E is not a proper subset of F. E is a subset of F, but it's not a proper subset. And vice versa. So F is not a proper subset of E, but F is a subset of E. So try to keep that in mind, and the comparison to the less than or equal to sign and less than sign is great. So a subset is just like less than or equal to, and a proper subset is like just strictly being less than. Okay, so I want to give you some practice with this, and that'll be in the next slide, just 2 more conventions to talk about using examples with English. We say 2 sets are identical if they have the exact same elements. So when you have something in list notation and something in predicate notation, and they're the same set, then of course these are equivalent. So the set containing this variable x, such that x is an English vowel, is the same thing as the set containing a, e, I, o, and u. They're the same set. The left side is list, and the right side is in predicate notation. You also find this with active and passives. So the set of x, such that x loves Mary, so these are all the agents that love Mary, is the same thing as the set of x, such that Mary is loved by x. So again, these are all of the agents such that Mary is loved by that agent. The difference between this is active versus passive. But another thing to keep in mind is that it does have to be the same thing. So these are both the agents of the sentence. These are the people doing the loving. Okay, and formally, if 2 sets are identical, like A equals B, this just means that A is a subset of B and B is a subset of A. So in other words, the elements are exactly identical because both of the sets overlap. So again, A, E, I, O, U is the same thing as the set of x, such that x is an English vowel. So that means that A, E, I, O, U is a subset of the set of x, such that x is an English vowel, and the set of x, such that x is an English vowel, is a subset of A, E, I, O, U. And I had an extra little bracket there that shouldn't be there. Okay, that's just definitional. So if A is equal to B, then A is a subset of B, and B is a subset of A. Now let's do some practice. Pause the video, try it yourself, and I will run through the answers right now. Okay, I think it's good if I draw these things out. So I'm always going to draw the rightmost set out. So we have S, B, A, E, G, I. I'm going to put C over here just because I know what to do in this question, so I have a bit of an advantage drawing this out. Okay, so this is our main set. This is our right side set. Now I want to ask, is the set containing ABC a subset of SBAEGIC? Well, if I can draw a circle around ABC and it's contained in this larger pink circle, then yeah. Okay, let's try this. B, A, and C. Okay, yeah. A, B, and C are all contained in this larger set. So this is true. Now, you don't have to do this visually. What you can do is you can check. Okay, A is on the left, so is A on the right? Yes. B is on the left, so is B on the right? Yes, it is. It's right here. Now, C is on the left. Is C in this right set? Yes. Okay. So everything on the left side is on the right side. Therefore, we have a subset. Okay. Let's try the next example. Okay, this is true. Let's get rid of our green circle over here. Okay, A, B, and J, is that a subset of the set containing SBAEGIC? Well, let's do this without visualization first. So A on the left, A on the right, we're good. B on the left, B on the right, we're good. What about J? J's on the left, but I don't see J anywhere in that larger set. So the answer for this is no, false. It is not. The set containing A, B, and J is not a subset of the set containing SBAEGIC. And if we were to draw this, let me just get rid of these marks here. If we were to draw this, we'd have to add J out here, and then we could circle this like this. So as you can see, the green circle is not contained in the larger pink circle. Therefore, no, we do not have a subset. So that is a visual way of doing this. Okay, we're done with that, with those larger sets now. Let's take a look at 1 and 0. So 1 and 0, this is our set, and we're asking, is 0, 1 not a proper subset of 1 and 0? Okay, well, if I circle 0 and 1, oh, this is the same circle. This is the same circle. But I'm asking about a proper subset here, right? So this is like the less than sign. These cannot be equivalent. So The answer is, this is true. This is not a proper subset. It's not a proper subset because the sets are equivalent. So the sets are equal. If it's a proper subset, then we would have to have less elements. So, for instance, the set containing 0 is a proper subset of 0 and 1 because the sets are not equal. Or the set containing just 1 is a proper subset of the set containing 1, 0. But because these two sets are equivalent, they're not proper subsets. Okay, just to bring you back to the element stuff, let's take a look at the set containing B and C. I'm asking, is B an element of the set containing B and C? Yeah, it's true. I find B in there, B on its own. That's what we're looking for. So just a little review from last video. Okay, and E, is the set containing F and G in a proper subset of the set containing F, H, and G? So F, G, H. Okay, well here's the large set, F, G, and H. Can we do F and G together? Okay, yeah, F and G is contained in that larger set, and it's not exactly the same. So yeah, this is true. Because F is in this set, and G is in that set, and it's not the exact same set. Okay, here's some more theoretical questions. If you have a set A, is it a subset of A? So is a set a subset of itself? Okay, well imagine I have, let's just pick 3 elements just for fun. It can be any elements we want. Okay, let's put a circle around this and let's call this A. So is a set A a subset of A? Well, if we draw another circle and we call this A, yeah, okay. Every element in A is also in A. The sets are equivalent, and this is okay because this is just a subset. So yeah, this is true. A set is always a subset of itself, because every element in that set is already in that set. Remember the definition of a subset. This would be if we have some element x that is in the set A, then we're also saying that x is an element of A. Okay, well this is true. Every element in A is always also going to be in A, therefore A is a subset of A. So a set is always a subset of itself. G, is the empty set a subset of A? Okay, let's try this again. Let's draw a set A. This time I don't care what's in it, but let's just put some elements in here for fun. Why not? 1J and B. Sorry, AJ and B. Okay, is the empty set a subset of any A? Well, what does the empty set have? The empty set has nothing in it, right? So, there in red is the empty set. It's got nothing in it. It doesn't matter if A has anything in it or not. The empty set has nothing in it. There's no elements to check. Therefore, by definition, always, this is true. The empty set is always a subset of A, because no matter what set you have A, it's always possible to grab a set with nothing in it. So if A has no elements, then there's no elements to grab, so it's a subset. If A has 1,000 elements, you can always pick none of them. So the empty set is always a subset of any set A. Finally, the last question. If A is a subset of B and B is a subset of C, then is A a subset of C? Okay, let's try this. So we have a set A, and this is within a set B. Okay. We have a set B, and this is going to be a subset of C. So C will be larger. Or it might be the same size as B. Is A in B? Or sorry, is A in C? Yeah. That's true. Because remember, if we think about less than or equal to, let's think about this. If 3 is less than or equal to 4, and 4 is less than or equal to 5, then is 3 less than or equal to 5? Well, the answer is yes. What if these are all the same number? If 3 is less than or equal to 3, and 3 is less than or equal to 3, then is 3 less than or equal to 3? Yeah, it's the same thing. So, if you think about the subset being like this less than or equal sign, then it's a little bit easier to think about these more theoretical things. But anyway, that's it for this subset video. Again, this is math. This is a little bit more difficult than what you're used to. But with enough practice, with enough examples, you'll get this. There's lots of examples on Canvas that you can try. If you want more, just ask for more. email me or post it on the discussion board. I am happy to give you as many practice problems or examples as you need to understand this stuff. So do not be afraid of asking for more questions if you need more questions.